Alright? Let's take a look at class example program, Unit D1, the very first example program of Unit D1, page 3. Okay. This is a very, very simple program, yet I'm going to show you every single detail of how to apply governing equation called continuity. Okay. So here's the problem. This is the horizontal pipe. Air is flowing from left to right. Okay. So air flows steadily between two cross sections in a long straight section of 0.1 meter inside the diameter pipe. Okay. The static temperature and pressure at each section are given. P1, T1, P2, T2. If the average air velocity at section 1 is 205 meters per second, determine the average in air velocity at section 2. Okay. So let's take a look at the figure I copied from the program statement. So this is a pipe, flow in, flow out. Okay. So first of all, I want to define control volume. Okay. So I'm going to choose a fixed control volume. Containing position 1, position 2 as one of those control surfaces here. So this is the fixed control volume. Okay. One thing which is very, very important is as you choose the fixed control volume, you're going to automatically choose the control surface. So this is the control surface 1. This is control surface 2. Control surfaces are the control area of a boundary of control volume where you allow a property of fluid to come in and come out. So this is inflow. This is outflow control surface. Okay. So obviously this is section 1, section 2. Control surface 1, control surface 2. Properties given here. Static pressure P1 is 77 kilopascal absolute. Static pressure P2 45 kilopascal absolute. Temperature is given T1, which is 268 Kelvin. Temperature T2 is 240 Kelvin. Average velocity V1. Average velocity is 205 meters per second. Okay. So obviously this is a velocity V1 coming in. Velocity is a vector, so I'm going to specify vector notation B1. Magnitude of B1 is 205 meters per second coming from left to right, horizontal direction. This is obviously velocity vector B2. Magnitude unknown. We want to know the magnitude, average value. Okay. So one thing before we start moving on, it is important to define at each control surface the outward unit normal vector. So it's outward and outward at each control surface. Outward means outward from the perspective from the control volume. Unit means this is a unit vector and also this is a unit vector. Magnitude is 1. Normal means this is perpendicular to control surface or area. This is N1, this is N2. This is outward unit normal vector of control surface 1. This is outward unit normal vector of control surface 2. Okay, that's good. Then I'm going to apply governing equation of continuity. So let's start from this. Continuity equation. ddt control volume rho dV. Keep in mind this B is a volume B. I'm going to use the horizontal bar to differentiate. This is a volume, not the velocity. Okay? So this is volume B. Plus integral over the control surface rho times B dot NDA must be equal to 0. So this is the governing equation called continuity. Okay, so this is very, very important warning for you. I guess this is coming from Unit C, but you may have an idea, which is a fake idea, false idea, I have to say. Well, continuity says Q is constant. So Q1 is Q2. Let's start from there. I have to warn you right now, forget about this. Those are wrong ideas. This could be correct, but first thing is you start from here. If this is true, you can get this equation from here. That is most important. So you're not going to start from some equation which is built upon so many assumptions introduced by someone or in the past. Jump right on. Hey, Q1 equal to Q2, let's solve that way. Don't do this. If this is true, you can get the same equation from here. Then you can plug in the value and finish up the problem solution. Okay? Don't start from here. By the way, this is wrong equation. I'm going to show you right now. Okay. So how do we apply this continuity? First of all, let's go back to this problem statement. This problem is actually kind of nice because it says steady. So this is a steady flow. Steady flow really means, in this case, within the control volume we define, the mass of air does not change over time. So within this control volume we defined, air mass doesn't change over time. If that's really true, we can drop this down. Sometimes the program says so, sometimes program doesn't say clearly, but you can assume it. You can always ask a question in exam saying, can I assume this is steady flow? Unless it is the solution of the problem itself, I'm going to probably usually tell you, yeah, sure, go ahead, assume it's steady, or don't, you can't. Okay? But again, this is a steady flow. If steady, this is 0. This term indicates how much mass changes within the control volume. It's not going to change, so that means time rate of change is 0. Right? Okay. So here is my equation. Integral over control surface rho B dot NDA is equal to 0. Okay. So I simplified a little bit. Second step, this is a control surface. How many control surfaces do we have? We have control surface 1 and control surface 2 both. So we are going to apply this term for both control surfaces. So this equation really means integral over control surface 1 rho 1 B1 dot product N1 the A1 plus integral control surface 2 rho 2 B2 dot N2 the A2. We have two control surfaces. If you add them up, it's going to be 0. Okay. Now one thing I know, this is a straight pipe, constant cross-section pipe. This means that cross-section area A1 is equal to A2. Let's call that A. So I'm going to, again, let me rewrite this equation. This is integral CS1 rho 1 B1 dot N1 dA. Cross-section area is pi over 4 times diameter, which is 0.1 meter squared. That's cross-section area. Okay, which is constant between control surface 1 and 2. Okay? Alright, so let's take a look at the B1.N1, B2.N1. So let's just take a look at this picture here. At the control surface 1, you have a B1 incoming. This is outward unit normal vector. If so, suppose if you take vector dot product between B1 and N1, what do you have here? If you take a dot product between two opposing vectors, one comes with magnitude of B1, this is magnitude of 1. So this actually becomes magnitude of B1 itself, which is, let's call this B1. Okay? So that's what I got by taking the product. How about control surface 2? Okay, if you do the same thing, B2, take a dot product N2. This is going to be, sorry, let's go back. This is actually vector of opposing direction, so it's going to be minus, right? Sorry about that, minus. This minus sign comes in because taking a dot product between two vectors with an angle 180 degrees. Okay, so let me just add, where should I add? B1.N1 is equal to B1 times 1 cosine theta. In this case, cosine theta is cosine 180, so this is minus B1. So in other words, this is the case that this is, so this is V1 N1, and then angle theta is 180 degrees. Cosine 180 is minus 1. Okay, so that's why if you take out a product, it's going to be minus B1. So you really do know this is minus B1. B1 is being magnitude of velocity vector B1. If you do the same thing here, take a dot product B2 dot N2. Obviously, this is magnitude of B2 itself. Okay, because you're taking dot product of vector in the same direction. This is angle theta is 0 in this case. Cosine 0 is 1. So if you take a dot product between B2 and N2, magnitude B2 comes out. Positive B2, this is minus B2, B1, this is positive B2, okay? So if you integrate rho 1, which is the density across the cross-section 1, multiply by minus of the magnitude of velocity B1, take an integration over the area, which area you know, area of cross-section of a pipe. This one becomes rho 1 times minus B1 times cross-section area A. Is that right? This one now becomes rho 2 times B2 times A. If you add them together, it's going to be 0. If you integrate over cross-section area, you get area itself multiplied. You can cancel out area because area is constant. If you divide both sides by area A, area drops off. So what do you have here? You get equation rho 1 B1 is equal to rho 2 B2. What is this? This is density times velocity. Density times velocity is not the flow rate. Flow rate is velocity times cross-section area. So this is a proof of that. This equation is wrong. You can't use this equation. This is the actual equation you got from this equation. So this is quite important. Okay? So now, knowing this is true, if the velocity V1 average value is 205 meters per second, what is V2? In order to discover that, you need to find out what is the density, what is the density. Can we get the density out? I guess the answer is yes. That's why pressure and temperature is given. So we can apply equation of state of ideal gas P equal to rho 1 T to find out rho 1, rho 2. Okay? So let's move on. So we are going to apply P equal to rho RT, equation of state. In other words, rho equal to P over RT. So rho 1 is P1 divided by RT1 multiplied by velocity V1 is equal to P2 over RT2 times velocity V2. Once again, gas constant is a constant value. You can cancel out both sides. Okay, so now the equation becomes P1 over T1 is equal to P2 over T2 multiplied by V2. From here, V2 can be given by P1 over P2 times T2 over T1 times P1. So we can plug in the values. Make sure you are using P equal to rho RT as an equation. Okay. If you use this equation, P must be absolute pressure, T must be absolute scale temperature. Let's go back and make sure. Oh, okay. P is absolute pressure, T is absolute scale Kelvin. Same here. If this is given as a gauge pressure and gauge pressure, you have to convert it to absolute pressure using local atmospheric value PATM. Okay, let's be careful. So knowing that those P and P are absolute pressures, this T and that T are absolute scale temperature, you just plug in the value as is. So this is P1, 77 kilopascal. P2 is 45 kilopascal. Okay, units cancel out. Multiplied by temperature ratio. T2 is 240 Kelvin. T1 is 268 Kelvin. Once again, units cancel out. Velocity V1 was given 205 meters per second. So this is going to give you 314.13 meters per second. All right. So let's go back to this picture once again. Important thing here, right here. Important thing, like I said, do not believe this is always true. Flow rate in is equal to flow rate out. So let's think about where does that equation come from. It is coming from here, obviously. Okay. So how do you get this one? Well, if the flow is steady, of course this one drops off, sure. Okay? Then you get that equation. And this equation can be applied in control surface 1, control surface 2. Okay. So if this is not the air, but it's liquid flow. If the flow is liquid, you can say density rho 1 is same as density rho 2, it's incompressible fluid. So you can cancel out density. Then you are going to have this kind of equation. if flow is steady, you get that. Then also, if fluid is incompressible, which is liquid, most likely liquid can be considered as incompressible fluid, which density doesn't change, then you can cancel out rho. The equation now becomes E dot NdA is equal to 0. Now this really means that integral CS1 B1 dot N1 dA plus integral CS2 B2 dot N2 dA is equal to 0. If you move on, this is going to be minus B1, and then integration gives you cross-section area A plus B2, cross-section area is 0. Cross-section area cancels out. By the way, this is the equation Q is constant, right? This is the equation Q1 equals Q2. Now this is the case that cross-section area is even constant, so this actually tells you, oh, velocity V1 is equal to V2. So let's go back and take a look at it. If this is a liquid flow, water flowing from left to right, if the velocity V1 is something, I don't know, it's not going to be this high, but velocity V1 is certain meter per second, velocity V2 is exactly equal to that. If you have an incompressible fluid flowing in a horizontal pipe of constant cross-section, continuity basically says that the velocity is constant. That's not true for this case. What's going on? This is air. Air changes density. If the density change happens, velocity changes. Okay? So obviously, it's a very, very big mistake if you choose this equation for this particular problem. Alright? So let's be careful. Let's stop.